Hey guys, I think at the end of my last video, I told you we were about to take a test, and we are, but we do have one more section called optimization. Now, as you have probably figured out by this point, learning how to do calculus through a video is probably not optimal, and it's not. And this is one of those sections where being face to face would be great, but if we don't have that option, which I'm assuming we don't since we're on video, this is one where we just take it step by step. And you're going to want to have some sticky notes, different colored pens. And if you have any questions, please make sure that you make a note of those. You will find as you look through the notes that you see here, I've done some underlining. I have done some prep work, which means I've gone ahead and done kind of the algebra, which will lead you into the calculus. Um, so if you need to, or I should say when you need to, because you will, just pause the video and then go ahead and catch back up. Okay, so what we're doing in optimization is we're going to make everything either maximized or minimized. In this particular case, you need to make sure you read the problem carefully first, identify the quantity to be optimized, maximum or minimum, and the constraint, which is your domain. What can your value not be? What can your value be? And if a quantity is stated to be a fixed value, this will be part of your constraint, which must be true regardless of your solution. So what we're going to do in problem number one is we are going to find two positive numbers such that the sum of the first and twice the second is 64. And then their product is a maximum. So we're going to let x equal our first number, and we're going to let y equal our second number. And according to our problem, the sum of the first and twice the second is 64. So the sum of the first and twice the second is 64. And we want the product to be maximized. So that would be xy. So we're going to solve this for y. And we want our product to be maximized. So f of x equals x times the value of y. We're going to do that product. And we're going to simplify. And we're going to simplify so that it's very simple for us to find our derivative. And setting that derivative equal to 0 means x is 32. So we're going to plug 32 into here. 32 plus 2y is 64. 2y is 32, so y is 16. So our two numbers are 32 and 16. A lot of algebra there. Really about the only calculus that you have is your derivative. Giving you some information here for number two, a rancher plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters, that's your area, in order to provide enough grass for the herd. What dimensions would require the least minimum amount of fencing if no fencing is needed along the river? So you don't need any fencing from here to here. So we're going to call this value x and these two values y because they are the same. So the formulas we're going to be looking for are perimeter, which equals x plus 2y. That's how much fencing you're going to require. You must use 180,000 of them, which is your area. So area is going to be x times y. So we're going to substitute that value, 180,000. We're going to divide by x and solve for y. And then we're going to substitute. So P of x, our perimeter, is going to be x plus 2y. And we're going to get rid of these parentheses. And we're going to find our derivative. That's 360,000 x to the negative 1, so negative 360,000 over x squared. There's our derivative. Now we're going to set that derivative equal to 0. And we're going to solve for x. There's no need for the negative here because we can't have a negative value. So x is going to be 600 meters. To find y, x times y equals 180,000. So we're going to use this formula here. So we have 180,000 equals x times y. So y is 300 meters. Now we're going to prove that we have a minimum. And we know really that our domain just has to be greater than 0. So we've got our 600 meters. We're going to prove that we have a minimum. So we're going to plug into P prime of x, and I'm just going to choose 400 and 700. And P prime is here. Again, we're proving that minimum. So 400 stored as x, 1 minus 360, 0, 0, 0, 0 divided by x squared is negative. And then 700 stored as x is positive. And negative to positive is a minimum. So therefore, we can say the dimensions are 600 meters by 300 meters. So that justification, if you were to see this problem on the AP exam, you would have to have that justification there to have full credit. If you want to take just a minute and jot down the information there for example 3, you may want to pause your video for just a second. An open box is being constructed from a piece of sheet metal 18 by 30 inches by cutting out squares of equal size from the corners and bending up the sides. What size squares should be cut to make a box of maximum volume? And then what is that volume? All right, so we're cutting up the squares with x. Total 18 minus 2x, total 30 minus 2x. So our volume is length times width times height. So x times 18 minus 2x times 30 minus 2x. X times your FOIL method, and then distribute. And you want that volume formula so that it's easy to take your first derivative. Set it equal to 0, taking out the 12. And because that's not factorable, we're going to complete the square. So we're going to get rid of that 12 by division. 0 divided by 12 is 12. So we have x squared minus 16x plus blank equals negative 45 plus blank. Middle number, 16 divided by 2, 8 squared. 8 squared is 64. And factor as a set of parentheses squared. And this is 19, which you can go ahead and bring over to set it equal to 0. And what that's going to allow us to do is solve for x. So actually bringing that 19 over didn't really help me. I'm going to take it back. Square root and solve for x. Now, one thing we haven't established, which we're going to do now, is our domain. So we know that this can't be, well, we know first of all that x can't be 0. We know that this can't be 0 and this can't be 0. So we've got to start at 0, but we can't include 0 because you can't take out 0. So 18 minus 2x, what would make that 0 would be 9. And what would make that 0 would be 15. So we need the lesser to make sure we don't get any negatives. So with that being the case, we're going to use our calculators and calculate these values to see if they're in our domain. So that one's 12.4. So that one would not be in our domain. And that one is 3.64. So that one is in our domain. So this is the one that we are going to focus on. And if you want to make a note there, it's because this one is in the domain 0 to 9, and this one is not. So our next step is going to be to find the volume at that value. So 8 minus the square root of 19, we're going to store as x. We're going to plug that into our volume. So 4x to the third minus 96x squared plus 540x. And that's our volume value. It's one of the pieces we have to find. And we'll just round that, and that is inches cubed. So next we're going to prove that we have a maximum. So we said this value here was 3.641. Found that in our calculator. So I'm going to pick 3 and 4, plugging them into V prime. So 3 store as x, 12x squared minus 192x plus 540. That gives me a positive. And plugging 4 in, I'm just storing it as x, 12x squared minus 192x plus 540, and that gives me a negative. I am looking for a maximum, and positive to negative gives me that maximum. So now we're going to write our answer. The volume, approximately 886.552 inches cubed, will be maximized by cutting squares from the corners of sheet metal that are 8 minus the square root of 19 inches, because v prime of x equals 0 at x approximately 3.641 inches. And the signs change from positive to negative here, which we proved in our chart. So basically what this strategy is it lists out in words what we're doing stepwise in these problems. So take just a minute and read those, and we're going to head on over to example 4. Again, I've done some setup here. What are the dimensions of an aluminum can that hold 40 inches cubed? That's your volume of soda, and that uses the least amount, minimum, of the aluminum. Assume the can is a cylinder and is capped on both ends. So you need surface area, 2 pi r squared plus 2 pi r h, and the volume formula pi r squared h. Solve for h, and you get 40 over pi r squared. And what you're going to do with that is plug it into the surface area formula so that everything is in terms of one variable. So the surface area is 2 pi r squared plus 2 pi r h. And then you're going to simplify. 2 pi r squared plus pi's cancel. One of your r's cancel. 2 times 40 is 80 over r. So from here, you're going to find your derivative. Surface area prime. And that's 4 pi r. And that's 80 r to the negative 1, so minus 80 over r squared. All right, so we're going to set that equal to 0. So we have 4 pi r equal to 80 over r squared. Just going to squeeze this in here. That's 4 pi r cubed equals 80. R cubed equals 80 over 4 pi. So 4 goes into 80 20 times. So r is the cubic root of 20 over pi. And if you were to type that into your calculator, you would get a value of approximately 1.853 inches. Now, we're going to prove that's a minimum. So 1.853 using the numbers 1 and 2, plugging into surface area prime. 1 store as x. So 4 pi x minus 80 over x squared gives us a negative. Storing 2, plugging into SA prime gives us a positive. Negative to positive is our minimum. So we have our R value, and now we need to find H. So H is 40 over pi times the cubic root of 20 over pi squared. And using your calculator there, you get 3.707 inches. So now we're going to write our answer. The can's measurements, and I'm going to go into the diagram for sake of space. R is approximately 1.853 inches, and H is approximately 3.707 inches, with volume 40 inches cubed of soda. Since S prime of 1.853 equals 0, and surface area prime changes sign from negative to positive here. We didn't establish our domain, but really the only thing we have to know about our domain is that your surface area has to be greater than 0, and we know our volume was 40 inches cubed, which we had already worked with. You're probably noticing that in these optimization problems, first of all, yes, they're all word problems, and second of all, they all use some kind of a formula that I have given you. So they are formulas that you need to be familiar with. I'm not going to say necessarily you need to go out and memorize them all, but we're using the distance formula in number 5 to figure closest points, and that is something that you should definitely know. All right, so we're going to plug into the distance formula. Which points on the graph of y equals 4 minus x squared are closest to the point 0.02? We're looking for closest points, which will be a minimum. So on our chart, we're going to be looking for that minimum sign change. So we're going to plug in square root, and we've got our formula and our point. So x minus 0 squared plus 4 minus x squared minus 2 squared. So x sub 2 minus x sub 1, and then y sub 2 minus y sub 1. So we're going to clean that up a little bit. And we're going to get the x squared, and this is going to be 2 minus x squared squared. Take a space. I'm just going to go out here to the side. So that's x squared plus 4 minus 4x squared plus x to the 4th. And then finally, we get to our distance, which is x to the 4th minus 3x squared plus 4. Now, a little note here. You can use the radicand to find the smallest critical values. So we're going to declare our function g of x or f of x, whatever you want, as x to the fourth minus 3x squared plus 4. Find your derivative. Set it equal to 0. And so x is going to be 0 and plus or minus square root of 3 over 2. So we're going to look at our chart. And on our chart, we're going to have negative square root of 3 over 2, 0, and square root of 3 over 2. And you're going to plug those into G prime. So if you will take just a second and figure out those test values and figure out your signs. These are the ones that I chose. And the signs that I found, we are looking for minimum values. So you have a minimum that occurs here, negative to positive, and that occurs here from negative to positive. 0 would be a maximum value. And remember, we're looking for closest points. So the next thing that we need to do, we'll call that step 3. The next thing we need to do is find f of both square roots of 3 over 2. And because it's squared, that's why I'm able to write it like this. So 4 minus the square root of 3 over 2 squared. And that will accommodate the plus and the minus, because when you square it, it becomes positive, and you get 5 halves. So it's time to write our answer. By the second derivative test, g double prime of x is greater than 0 for all x. So the closest points to 0, 2 on the graph of y equals 4 minus x squared are, there's our y, there's our x. So negative square root of 3 over 2, 5 halves, and square root of 3 over 2, 5 halves. So on your graph, they're approximately there. All right, these last two examples are fairly long, so I have gone ahead and given you some information here. If you want to take just a minute and write those down. The training facility for a sport club is situated along a straight shoreline. You row your kayak out 2 miles from the nearest point on the shoreline, and then row 6 miles down the beach each day to train for an event that includes rowing and running. If you can row at a rate of 3 miles per hour and jog at a rate of 5 miles per hour, what is the least minimum amount of time required to reach the clubhouse? How far from the clubhouse should you beach your kayak? So your domain is from 0 to 6 because that's the farthest point that you're going to be from where you started. And to find our hypotenuse here, that value, you just do the Pythagorean theorem. X squared plus 2 squared equals c squared. And then the square root is x squared plus 4. The whole value is 6. So this piece would be x and this piece would be 6 minus x. Distance equals rate times time. The total time is the row time plus the jog time. So your formula is your row distance divided by time plus your now jogging distance divided by time. So now we're going to find t prime. So t prime of this, I just kind of am going to do out to the side. So that's 1/3 times x squared plus 4 to the 1/2 power. Take the derivative and you get 1/6 times x squared plus 4 to the negative 1/2 power times 2x. And that's x over 3 square root of x squared plus 4. And then your derivative here, 6/5 is a constant, so negative 1/5. All right, we're going to set that equal to 0. Go over here where I have a little bit more space. So x over 3 square root of x squared plus 4 has to equal 1/5. Cross multiply. To get rid of that radical, we square both sides. Distribute the 9 and you get 9x squared plus 36. So that's 16x squared equals 36. Divide by 16 and reduce and square root. Again, you don't need the negative. You're not going negative miles. So that's approximately 1.5 miles. And just a little bit of simplifying out to the side. All right, so now we're going to do our chart. Remember, we start at 0 and go to 6. And we have our 1.5 in the middle. So choosing values 1 and 2, plugging them into T prime gives you negative and positive. Now, I know I went through that quickly. I did not show you how and why that works. You need to be checking in your calculator to understand where those values came from, because you're going to have to be able to put those signs in your chart to prove indeed that you do have that minimum or maximum that they're asking for. In this case, it would be a minimum. So the least amount of time is T of 3/2, which when we plug that in gives us approximately 1.77733 hours. And that's if you beach the kayak at 1.5 miles, since T prime of 3/2 changes sign, look at your chart, from negative to positive. In the grand scheme of things, these are not that difficult. There's just a lot going on, which you will definitely see here, for example, number 7. Justin Case found a 4-foot piece of wire left on a construction site. He's learning about optimization and calculus and wants to cut the wire to create a circle and a square. How much of the wire should be used for each shape in order to maximize the total area? So a couple of things to write down here, first of all, and you're going to want to pause the video because I've got a lot of preliminary information here. The area of a circle is pi r squared, circumference 2 pi r. Circumference is like the perimeter of the circle. So the circumference is what you're going to be looking at to determine how much wire you use. Area is s squared, perimeter is 4s. So with 4 feet of wire, the circle circumference plus the square perimeter has to equal 4. For the total area, area of the circle plus area of the square is A equals pi r squared plus s squared. The domain has to be, the side value has to be between 0 and 1 because you only have 4 feet of wire. So the side value of the square must be between 0 and 1. Circumference is 2 pi r. If all we used was the 4 feet on the circle, then the radius would be 2 over pi, which means the area for that would be approximately 1.273. That's the area for your circle. So we're going to solve for r. 4 equals 2 pi r plus 4s. That's your maximum amount of wire equals the total area. Solving for r, you get 4 minus 4s over 2 pi. substitute to get the equation for area. Area is 4 pi r squared plus s squared, which we found at the top of the page. Substitute the value for r. Simplify. This is 2 minus 2s over pi. Just divide by 2. Pi times 2 minus 2s over pi squared plus s squared. FOIL it out and square pi. Pi over pi squared is 1 over pi times your numerator. Find a common denominator and simplify. So that is your area formula revisited. So this is going to be your area formula. Now we're going to find that derivative. It looks bad. It's not as bad as you think. Remember, 1 over pi is a constant. 4 plus pi is a constant. There is no product rule here. Okay? All right, so we're going to keep our 1 over pi on the outside. The derivative of s squared is 2s times your constant. Derivative of negative 8s is negative 8, and the derivative of your number is 0. So that derivative actually looks a lot better than that area formula. So divide or multiply by pi on both sides gives you 0 and eliminates your fraction out front. So you have 2s times 4 plus pi minus 8 equals 0, so equals 8. If 1 over pi can't be 0, so if what's in your brackets equals 0, then your whole function will equal 0. So divide by 2. So s is equal to 4 over 4 plus pi. Type it into your calculator and you get approximately 0.560. Looking at your chart, you are looking for a maximum, so A prime. We're going to choose 0.1 and 1. We're plugging these two values into A prime of S, and you get a negative and a positive. Negative to positive is a minimum. We need a maximum. So we're going to go back and we're going to look at A of 0. So if we plug 0 in for A, here's A. Plug 0 into A for S. You get 1.273. And I'm going to show you how all this works. Back into that formula, plug in 0.560, and you get 0.560. Again, use your calculator, store these values, find it, and check that these are indeed correct. And then if you plug in 1, you get 1. So looking at these values, this would be a maximum and this would be a minimum. So interpreting what we have found might give you some interesting results. So if the length of the square is s equals 0, can't happen, then area is maximized. You just saw that right here. A maximum right there. Side equals 0, maximum value. So therefore, the total area will be maximized if he uses all the wire to do what? Can't have a square with a side measure of 0. Uses all the wire. Oops, I've already done all that. Uses all the wire to create a circle. That's the only way that this problem will work in terms of using the wire at its max. take a look at these problems, reread that highlighted information, especially the strategy for solving optimization problems. Notice in each of these problems, you have to prove that you indeed have your maximum or minimum in order to make sure that you have done everything in order to solve the problem. Let me know if you have any questions. We will talk about those. Now I can say that you're definitely going to have a test coming up, and that chapter 5 is definitely over in terms of sections. I hope you guys have a great day, and I'll see you soon.